So hello, sorry. Hello everyone. Today we have the pleasure to have as speaker Professor Michael Wallner from Austria. The topic of research of Professor Wallner is around analytic and enumerative combinatorics, and in particular in interaction with probability theory, number theory, and interdisciplinary applications in computer science and computational biology. It has studied lattice paths in one and higher dimension, tree-like structure like directed ICT graph, deterministic finite automata, and phylogenetic trees, as well as Young tableau and permutation patterns. The methods that he specialized includes combinatorial methods like generating function, the symbolic method, and bijections, analytic methods like singularity analysis, saddle point analysis, and kernel methods, and probabilistic methods like the method of Momans generating, like the method of Momans and martingales. The talk of our speaker today is entitled combinatorics of non-deterministic works. Thank you again, Professor Warden, for accepting to give us a talk, and please, you can start.
Thank you very much. Thank you very much for this very kind and long introduction. And indeed, you will hear today some of the topics you mentioned today. So there will be something about lattice paths for sure, because it's already in the title. And there will be as well something about analytic combinatorics, enumerative combinatorics, and the kernel method. So let me start with the motivation of what I want to talk today. So basically, what I want to do, and just to let you know, if there is anything that you don't understand, or if something doesn't make sense, please let me know and just interrupt me anytime. So just let me know if there's anything which you want to know. Right now, there's quite some noise. I hope you can still hear me. I think it's just from one of the other audiences. I think it's better now. Perfect, thank you. So let me start with an introduction. So basically, this research started with some colleagues when I was in Bordeaux, and I was discussing there some things about networking, or they were working on networking. So the idea is the following. We have given a network, and we want to transmit a message. Let's say we are at the beginning at this one. This is the sender. He wants to send this message through the network. You see it here. And during these points should denote some routers, which talked with each other with using different protocols. And these protocols are such that basically they can only talk with each other when they're able to encapsulate and decapsulate their messages. So this means basically that this is denoted here by this blue or red circles, meaning you put them in a capsule, you put them into you add a header and a tail actually in a sense, and then send it and maybe encrypt it and send it over the network. And here it should denote that the blue ones use the blue protocol and the red ones use the red protocol. And then some of them, like this node here in the middle, has a blue and a red dot. It uses both protocols. And the question is now, what is the probability that a message can be transmitted through this network from the left to the right to the person who wants to receive it, such that at the end he can read it again if, for a given network topology, we use the encapsulation abilities, we assign them randomly, basically uniformly at random. So this is studied empirically on many topologies with many protocols, and we wanted to work on it more on a fundamental level. And for this, we simplified the problem in order to make it possible to work on it. And basically, the first thing we did, okay, what is the simplest possible model we can look at? And the simplest topologically is the simplest model is just a line, as you see here at the bottom. So we just have a line graph so that you can think of them as servers on a line. They always hand over their message. And what they do, they receive something and then they either encapsulate. They can encapsulate a couple of times and then maybe decapsulate. And we want to know if these capabilities are assigned uniformly at random on this line with just one protocol, what is the probability that at the end we can read the message again, given that we can only add one layer or remove one layer. So the ideas which are used here, they're used in when you want to transmit over IP4, IP6 protocols, when they want to should talk with each other. It's used in virtual private networks. Onion routing actually is using this for privacy, that it encapsulate multiple times with the same protocols and so on. But I want to work on the mathematical fundamentals of this problem. And the idea of this simplified and actually toy model here is to explore first what can be done and develop some mathematical tools behind this. So this is our model. Let me focus on this now. You see the line again. And what it will be, we will define something which is called non-deterministic tick walks. So here I added additionally in the blue circles an E or a D, meaning that this node can now, this is not just for this is a random assignment, it can encapsulate, or it encapsulates, so it puts a blue bar around it. It maybe encapsulates second time, a second blue bar, and the D means that it decapsulates, it takes one blue bar away. And basically this ED is just basically a word in letters, EED. And at the end, what we are interested in is like that at the end, we come back to the ground state. And this is encoded by the fact that what we have, this is actually a DIC language in classical combinatorial terms, or it can be encoded in terms of a lattice path in terms of a DIC path, which you see on the bottom left. And here what we do, a +1 encodes an encapsulation and a -1 a decapsulation. And then this path starts at 0, ends at 0, and never crosses 0 because we cannot decapsulate if there's nothing. And this is this simple language. And the process over this network here is just the 1, 1, -1, 1, -1, -1 sequence. And
Sorry.
now, please.
Just a question. The word EEDEDD is generated randomly or
it will be then at the end, we will then assign probabilities to the capabilities. So we will say it's probability 1/2 for a E and 1/2 for a D, and then look at it. And maybe probability for one node that it can do this one, or maybe. And then according to this probability, to this distribution, it will be distributed. But you can think of it at the moment completely random and equal this probability for each choice. Okay, thank you very much for this question. And this brings you exactly at the right question, because here at the right point, because right now it's, well, everything is deterministic. It's either possible or not. But what we additionally allow, we allow that some, of course, some of them can do both. They can encapsulate and decapsulate. And this brings us now to this, what I marked here in red, to the non-deterministic DIC paths. And in the non-deterministic world, what we do, we have step sets as well, but now our steps are sets itself. So the step -1 is a set -1, just consisting of the singleton 1. The jump +1 is a singleton, just a +1. And then we have the capability to do both. We have a set which is now a -1, 1. And then a sequence of such steps is a non-deterministic walk in this model, and I call it a non-deterministic DIC walk if it's using exactly this step set. So here you see an example. And what's happening in the world of paths, you can visualize it in the sense that you follow all trajectories simultaneously. So we have a +1, for example, here, and then here the next one is a -1, 1. This is this red one. So this splits. It's like a branching random process. But basically what we're interested in, we want to understand at the end what's the probability to find one trajectory which comes back to the x-axis at the end and stays, for example, always above the x-axis. And this is the objects we are interested in. This is the objects we want to analyze. And here the non-determinism means more like simultaneous, like we traverse the walk simultaneously in all different trajections. It's not random in the sense of here. There will be random probabilities for each of these steps. But so not the randomness comes from probabilities for each of these steps. But the non-determinism comes from the fact that we're interested in following the trajectories all simultaneously. And we say then that this path is of a certain type if at least one of the trajectories is of this type. So let me make this a bit more clear. We look at different types of walks. So as in the classical terminology, we say that we call it just a walk if it's completely unconstrained. It can do whatever it wants. We can append them. We start at 0 and we append a certain number of steps. And this is what we say. And we call it an N walk, a non-deterministic walk, if there is at least one not classical walk in the walk. So you see one on the bottom left. So we can just do anything and there will be always like at least one walk in there. I marked it in red. I marked a classical walk in red, but there's other choices for it as well. More interesting is the case of bridges. A bridge, I mean a walk which ends at 0 again. You see one here in red, that's the second from the left. And I call it a non-deterministic bridge if the branching walk, the non-deterministic walk, contains at least one bridge. So for example, here we do like a -1, but then we do up, up, and you see the key property is that if we append a step, we append this step everywhere. We append the same step everywhere. For example, a +1 is appended in both of these trajectories of this path. And the top one ends somewhere else above the x-axis, but the bottom one ends on the x-axis again. And because of this, the full path is called an n-bridge. One of its trajectories is a bridge, then it's an n-bridge. In the same sense, an n-meander or a meander or n-meander, this is a path that says non-negative. It never goes below the x-axis. So basically you see an n-meander here. And for the n-meanders, like let's look at the top one. The top one is a good trajectory. It stays always, it never goes below the x-axis. That's okay. And the bottom path basically would go at this stage below the x-axis. I marked it here with this dashed gray line, so we just ignore it. We know we are interested in n-meanders, so we're not interested in this trajectory anymore. You can think of that this trajectory is now absorbed, it's lost, like because it's you cannot continue this trajectory anymore in order to have an n-meander. And the last thing is an n-excursion, and this is basically just a bridge and a meander at the same time. So I call it like this: if it ends at 0 and it stays non-negative. And we are interested in these 4 different types of walks. Okay, does the concept make sense? If there's any questions, please let me know, then I can explain it again. But this is the key idea of our non-determinism. And this is the walks we will analyze now. This is the classes we will look at. And the key is really that even though there's multiple paths in it, it's just one non-deterministic walk. Okay. Doesn't seem the case. So let's focus now on the simplest possible case. This is the stick walks, the stick n walks. And afterwards, I will focus as well in other cases, and I'll show you what we can do in much more generality. The key concept here is what is known in additive combinatorics as the Minkowski sum or the sum set. It's a very simple concept, a very simple idea. Basically, you just take 2 sets. If you have given 2 sets, we define the sum of it as the sum of all elements. So like this, A plus B is just the sum of all elements A plus B, such that A is in A and B is in B. This is what I call now. And we will need to work with these sets because we will need to understand what the walks are doing. Then let me phrase it again. I call it an n-step set if it's a finite subset of the power set of non-negative integers. So for example, on the right, I'll show you always I show you an example on the right. So here you say the dick n walks. So as I had before, -1, 1, and the step -1, 1. And here is an example. A walk is just a sequence of these objects. So here is an example sequence. And on the right, you see this path of length 3. This is a dick n walk. And the key concept where we need this sum, basically, this is actually coming from here, is the set of reachable points. So where do all trajectories end? This is also the key concept in the enumeration of lattice paths. We need to know how far away from the x-axis or where we are at this moment. And here we are at several points simultaneously. We are at several points in parallel. And this I denote by R of V. It's just the sum of reachable points. You just sum it up. And basically here the Minkowski sum comes into play. So it's just here, this for the path -1, -1, 1, -1, 1. You see here the sums. We have a -1, in parallel -1, 1, and then again in parallel -1, 1 to all points. So meaning at the end, my reachable points are the ending points, here denoted by the loose ends. It's just a set -3, -1, 1. This is where the path could continue. This is what it has reached. And we additionally define the minimum and the maximum reachable points because they will be the most important to characterize them. So for example, here, its minimum is -3 and maximum is +1. And with these concepts, what I can do, I'll now focus on generating functions for these objects. And let me encode here just for the unconstrained dick walk. So we just append any number of n steps for the dick n set by dxyt. So what do? In x, I encode the minimum of the reachable points. In the power of y, the maximum of the reachable points. In the power of t, the length. This is how far I've gone. And then I sum over all possible walks. So in the language of generating functions, this just means I have for walks, it's just a sequence of my possible steps. In the length is how often I use a certain step. So a sequence is a geometric series, so 1 over 1 minus t. So in t, I denote the length. And then how often do I use each step? How often do I use a 1? How often do you use a +1? And how often do we use a branching process, a branching step, a +1, -1? And this simply encodes into this generating function. So let me guide you through what's happening here. So what is a down step doing? If we have a certain minimum, just the down reduces the minimum by 1. So we have an x, we divide by x, and it reduces the maximum by 1. So we divide by y. This is this part doing. On the contrary, vice versa, it's the up step is increasing the minimum and it's increasing the maximum. So we have an xy because we go up. And the interesting part is now the branching. If we have both possibilities, then what's happening? The minimum will go down because we divide by 1. So it will, as you see here in the picture, basically the minimum goes down. In between something else is happening as well, but the maximum goes up. So we divide by x because the minimum is reduced by 1, and we multiply by y because the maximum is increased by y. And so we simply got this rational generating function, which is encoding these statistics. And what you get immediately from here as well, but obviously it's obvious here that, okay, because the walk is completely unconstrained, we have 3 different steps. So the total number of walks is 3 to the n, or in general, the number of steps to the n. So if s denotes the number of allowed steps. But this reasoning will always work. And this is the key, this is the starting point, this statistic to understand what's happening here. And what is quite nice with this stick and walks and with this representation as well, is that with these ones, we can also encode them or find make a bijection or a relation visible to classical 2-dimensional lattice paths. And this one we will use a lot because it will give us a nice intuition what's happening behind the scene, basically. So I just copy here again the generating function. So you see this rational generating function here, okay?
Just, I have a naive question, please.
Please.
Why the minimum cannot increase and the maximum cannot contrary? The minimum increases and the maximum decreases.
Yes.
We have the term x multiplied by y to the power -1.
Yes.
Why this term does not exist?
Why this case is not possible?
Yes.
Because in our case, what we'll do, and this is a very important, it's not naive, this is a key observation actually, Rafik, this is a very good question. The key what we do is we encode, we continue a path simultaneously in all loose ends, basically. So if we look at this example, if we do now a plus up, we will a +1. We will do a +1 in the lowest one, in the middle one, and in the top one. Meaning, you know, if the lowest one increases, the top one has to increase as well. No choice.
Okay, no choice.
And if the top one decreases, all the ones below have to decrease as well. Just if both happens, then this one increases and decreases, but the minimum for sure decreases and the maximum increases, and there's more points in between. But the key is there is some monotonicity here. Basically, there is no choice to do this because we always do the same thing at all loose ends. Does it make sense?
Yes, thank you.
You're welcome. So now we have this representation. And this representation here, basically, we can now use to find another representation of this object, what they're counting, because what we can do, we can interpret the minimum and the maximal change of these reachable points, as well as changes. And I used already x and y to kind of encode x and y axis, x and y directions on the plane. So basically what we do, a -1 was this term x -1, y -1. I don't know if you can see what I'm marking here right now, but it's basically this here. And I already jumped to the example. So we have the -1 was a -1, 1. And at the bottom on the right, you have the step set. So basically it means the -1 is sent to a change to x becomes smaller and y becomes smaller. So we have a jump to the southwest here. The 1 was a jump 1, 1, because x increased by 1 and y increased by 1. This is a jump northeast, so upright. And the minus 1, 1 was this x minus 1 to y to the 1. This is a jump, you can interpret it as well as a jump up and left, so northwest. And this path is then basically, if you want to count the number of paths, starting from the origin, which used these steps a couple of times, is exactly the same generating function. And this is the bijection. So basically, if you look at this left, if the non-deterministic walk on the left, it's bijectively mapped to this one. And up, a +1 is mapped to a 1, 1. So we do a 1, 1. Then it branches. A branching is mapped to a -1, 1. So it goes left up. And this is how it continues. So basically the non-deterministic dick walks are in bijection to classical two-dimensional lattice paths of the same length with this special step set. And we'll use that later on. So there is already a nice connection here. So what is now the key in order to count them, because at the end we want to enumerate them, is like to understand these reachable points for dick n walks. And let's start now. Dick n walks we have understood. Now it also go to dick n bridges. So I just recall the step set here. And we recall that an n bridge is an n walk containing a bridge. So you see an example on the right. And the key observation is now that the reachable points are always finite intervals such that they are spread out by 2. So basically you have always 1 point in between, and everything between the minimum and the maximum is there. So if you know the minimum and the maximum, and this is already why we chose this statistic, you know everything which is happening between, because for dick bridges and walks, in this case, they have to be 2 periodic. And here you see that. Why is this? You just see it simply by induction if you want. But basically, you see an example here. So if in red, let's say I had now at the end a +1, +1, +1. So it continued to be like 2 periodic. If I do a -1, it looks like this. So we go down, down, 2 periodic. And in the case that we have this fork, what's happening? Well, it's still 2 periodic. It's just a bit longer. But if you have the minimum and the maximum, you know the full pattern of these reachable points. And this is now enough to characterize n bridges in n walks. Because we have now this information, we know the minimum, the maximum, the length. And when is it an n bridge? Well, it has to return to 0. So what does this mean? In order to have a return to 0 here, they have to be of even length. Otherwise, it's impossible. You see here, this one has length 6, and before it had length 5, so then it's impossible because of parity to have a path which returns to 0. And then what we need, like here, we need that the minimum is below or equal to 0, and the maximum is above or equal to 0. And that's all we need. So this is the object. This is a characterization of n bridges in n walks. And the interesting thing is, this information we have. With this one, we can work. So let's do it. Let's get the generating function of dick n bridges. So this is the theorem for dick n bridges. We can show that the generating function, let's call it bxyt, is algebraic of degree 4. It's quite simple, actually. And if you sub in x equals to 1, y equals to 1, if you don't care at the end, because at the end, the minimum and the maximum are actually just artificial. We call them sometimes catalytic variables. We just need them to count, basically. But they have information itself, as we have seen in the bijection. But the generating function is very simple. It's given by this generating function. And its asymptotic growth, and this is what we were mostly interested in, is 9 to the n minus this term, which grows like 8 to the n square root 7 over n. What is quite interesting already here, let me first discuss this result a little bit. We see here in the asymptotics 2 different regimes. We have a 9 to the n, and then the next regime is already of lower order. It's an 8 to the n square root of n without other polynomial terms. So there is already what is behind this? There's 2 different singularities. You see it on the generating function. You have a polar singularity at 1 over 3 basically, but because it was of even length here, the n became its even length paths. And then you see a square root singularity, but this is just for the experts right now. But what is also interesting is the number of dick walks is 3 to the n, so the number of even length dick walks is 9 to the n, as well asymptotically. So this means asymptotically, a random dick walk is a dick bridge. So every n walk, if you just take anything, it will be a dick n bridge. And this is completely different than, well, it's a different model, but different than in classical paths. There is not the case at all. There's like an order n to the square root n less of them. So basically, the probability to have a dick bridge goes to 0, basically. But here it's probability 1. Okay, that's already quite interesting. So how to prove this? And here we use this generator, this bijection, this idea, and let me just sketch it because it's quite interesting which kind of phenomenon happened here. I had to play here. We just use the characterization from the previous page, basically, the simple one. So what we need the generating function of even length. Okay, this is easy to get. You easily get it by this transformation. You just kill all terms by setting t to minus t and adding it to the previous generating function. If you sum it up term-wise, you see that odd powers of t just vanish, and you have twice even powers of t. So you divide by 2. This is the generating function. I call it d2. And then in the second step, we said that if we have the even length generating function, I just need we just need x less than or equal to 0 and y bigger than or equal to 0 of this. So by this notation, I denote here that I want to have this extract exactly these parts. And here I want to emphasize that in general, I can extract. There's a lot of theory. There's a lot of things known about extracting coefficients, non-negative, positive, whatever special parts of generating functions. And in general, if you have to extract 2 things from a rational generating function, so if you extract 1, it's algebraic. But if you extract 2 in general, it's not algebraic anymore. It's still definite, meaning it satisfies a differential equation with polynomial coefficients. But here it's general, not definite. But here it's even very simple and algebraic. It's not algebraic in general. That's what I wanted to say. And what's happening here is that with this special step set, what we see, if we count walks, if we look at the walks, the characterization that x has to be negative and y has to be positive means that we end in the second quadrant, so on the top left. So meaning we have to be on the top left quadrant, basically, at the end. Okay, and if we have to end there. How can we express this in this special step set? Well, we take all walks and we subtract the ones which end on the right, which end below. And in general, we have subtracted now too much because there is an intersection. But for this special step set, there's no paths in the bottom right quadrant. And because of this, these 2 extractions are itself algebraic. And because of this, by closure properties, you just subtract 2 algebraic properties from a rational function, it stays algebraic. But it's a little bit, it's a special thing. It's a little bit a miracle, but it's a special feature of this specific step set. It tells you already some nice combinatorics, which are here in these non-deterministic walks. Okay, this was maybe a bit technical, so let me show you what else can be done. We have now looked at dick n bridges. We know the algebraic, we know the asymptotics. Let's look at the next interesting class, dick n meanders. So recall that the meanders is an n walk containing a meander, so never going below the x-axis. So an example is shown here. We do a +1, we do a +1 -1 in parallel. Then in here, I chose a -1, okay? Here in the gray dashed lines, I denote how it would continue, but you don't care. Actually, you can think of removing these parts. And in the future, I will not show the gray part anymore because if I want to look at n meanders, this part is gone. It's dead because we don't follow these trajectories anymore. We only follow the top trajectories, only the trajectories which go above the x-axis. And this makes n meanders a bit more complicated because you see, if I follow just one trajectory, it could die. It could die in the middle because I cannot continue anymore. And because of this, okay, I branched here, maybe I went down, but I would need to go up to the top, to this very peak at the second step in order to be able to continue in the future. So in a sense, we nearly need to know everything. So this seems much, much more complicated compared to dick n bridges. And for this, what I actually want to do, I want to generalize the reachable points because the reachable points are now not just the sum, but the sum conditioned to stay non-negative. And for this, I define a new symbol, the non-negative sum. I denote it here by this plus. I didn't find it. This is not the best notation, but it was at least the nicest one, making it nicely visible. And I won't have direct sums here in this talk. So this sum will be now the Minkowski sum, where we condition to be non-negative. So let's recall this and look at it, make it clear what I mean. So we look at n meanders. So we take a finite step set, a finite n step set. So let's look at dic n meanders again. We have a -1, a +1, and a -1, 1 in parallel, this fork. Then an n meander is a sequence of these objects, such that what is the key now, you see one here and depicted, such that the reachable points here, which I denote now by R plus, are the sum of this non-negative sum. So basically in each step, I have to condition to be non-negative. So for example, at the beginning here, I have a -1, 1 on the right, and I can only continue the +1. I cannot continue the -1. This was the gray one because this is going below. I'm not non-negative anymore. Then I continue from the +1 with another +1, and then I branch. And this gives me the reachable points for n meanders in this case as 1 and 3. And again, I define the min and the max of these objects. Okay? So a bit more complicated. A different sum is involved here. But as before, I define the generating function of dic n bridges, now with this d plus, where I encode these three statistics: minimal reachable point in x, maximum reachable point in y, and the length in t, in the t variable. And in order to understand this now, what we could show, even though it's much more complicated, it looks like the generating function is still algebraic, but a bit more complicated. And what's happening now? I need two auxiliary functions, x and y, to write it in a nice form. It's not important what they look like. It's just there. It's easy to write it down on the slides. And it satisfies this closed form where dxyt at the very end is the generating function of non-deterministic dic walks, basically. So with respect to this, I can do it. So how did we do this? And let me just sketch it. Basically, the idea here is, well, we have a decomposition of the dic n meanders when we consider different cases. So first of all, a dic n meander, we start at 0. Okay, so it's the only dic n meander of length 0 is the empty walk. So length 1 in the generating function, it's just the 1 at the very beginning. Then, in order to continue, I append a step. And now I could distinguish three different cases. Either I'm away from so I distinguish with respect to the minimum and the maximum. So either in the first case, the minimum is not 0. Okay, if the minimum is not 0, I'm away from this axis where I could die. So this means d plus xyt, the general case, minus the case where the minimum is 0. So I don't want the minimum 0. Then I just append the classical step. I can append everything and I continue. And I change the xyt accordingly. Then if the minimum is 0, I have to distinguish as well if the maximum is 0. Because if the maximum is 0, this is the third case, I cannot attach the down step. Because if the min and the max is 0, this means I just have a point on the x-axis. My reachable points are just 1 point. If I would go down now, I wouldn't be able to continue. And in this special case, I'm just allowed to continue with a +1 and a +1 -1. And now what I do, as before, I translate these steps in the changes on the minimum and maximal reachable points. And how does this look like now? Well, as before, the first case is the same. The second case is a bit different, but I want to go now into the full details here. But let me just show you on the last case what's happening. Again, I said that I can never continue the -1. So, okay, I can just, at the +1 is okay. So I do the minimum and the maximum increase by 1. And also, if I continue with this fork, in this fork, because I'm on the x-axis, I'm only allowed to continue with the top step, because the bottom step would also send me below. So this one is also the minimum and the maximum both increase by x and y, because I have to drop the minimum. And because of this, I have here xy, xy. And this gives me now a functional equation which characterizes this generating function. And this one we can use with the kernel method, which we actually have to adapt a little bit here because we have to use it twice. First in y and then in x. And actually, just for the experts, the x and the y of t, the top one, are actually the branches of the kernel you have to use in order to solve this system. But this was a little bit of a surprise as well, honestly, because intuitively, I didn't think that this would work. But now with the right catalytic variables here, the minimum, the maximum, you could really see these relations here, which are mimicking again what we see in two-dimensional lattice paths. And this is what I want to link this as well with. But first, we have a nice result. Let's look at some special cases. And if we forget x and y equals to 1, then we can look at the counting generating functions. So we don't care of the minimum maximum, just of the number of n meanders. This is d11t. And the generating function is given here. And it's actually a nice sequence in the OIS with connections with one-dimensional lattice paths, which we also explored in the paper. So if you're interested in these connections, they're also quite nice. We looked at them in the paper, and I don't have time to look at it right now. Then there is d01. This is a very interesting case. This is the guys. If we set x to 0 and don't care for y, this means that at the end, one trajectory has to end on the x-axis. Because of all reachable points, the minimum is 0. It can never go below the x-axis, but the minimum is 0. This means I can reach 0. Why, I don't care. I have something above. It could be there could be many reachable points or none, but this is what we call n excursions. And this is the ones we actually were interested in at the beginning for the networking motivation. And then the D00 is not, this is the cases where we return completely to 0, 0. This is the last case, meaning that the reachable points really returned to just a singleton. And here, this means we cannot continue except with upsteps anymore. And also these ones were in the OAS and have these nice generating functions. And what is here, again, with a singularity analysis from analytic combinatorics from these generating functions, because they are so simple, we can directly get asymptotics. We see here parities because something has to be even and so on. So because of this, but ignore these parts. I highlight in blue basically the asymptotic growth. And here again, what is interesting is there is a 3 to the n as a leading coefficient asymptotic, and then the other the asymptotics of the lower order, they are already much smaller. So it's a square root 8 to the n basically here, which is smaller than 3 to the n. And what is as well quite nice, because the 3 to the n is the exponential growth of the dick and walks. So the 1/2 here basically means that if you take a random dick and walk with probability 1/2, it will be a dick n excursion, n meander. And with probability 1/4, which is here in the second line, it will be a dick n excursion. And this is kind of answering now the networking motivation. So if on this line, if we have equal probabilities, the probability to have an excursion to be able to transmit, to encode a message and decode it at the end again is 1/4 in a setting where you take them the capabilities completely at random in a line, basically. And this motivation we want to continue now in the next setting. We want to look at what can happen for other probabilities. So let me first look at how many excursions are there actually if I look at an n excursion. So in a class, if we have this classical dick paths and this dick n excursions. And now what could ask, okay, if there is one, it already classifies the full path to an dick excursion, to an n dick excursion. But you could also ask, okay, like how many are there in general? And this is actually quite easy to answer, because you can easily count the total number of excursions. Let's say C2n is the total number of classical excursions contained in all n excursions. Then what you can say, this +1 -1 jump, this fork, it just means that you just either go up or down, and it will always be completely a different path. So it will be either you can interpret it as a classical up or a classical down path. Or vice versa, if you want to count, if you take a classical dick path, you can say that every up is either an up or an up-down, so the up part of an up-down, and every down is either a down or the down part of such a fork. So this just means for every up you have two choices, for every down you have two choices. So in a classical walk, basically of length 4, so for a dick path, it's the Catalan numbers, so they are even length. So you just have 2 to the 2 to the n more choices. So you just need to multiply with a 4 to the n. And now with this, I can look at the average number of classical excursions in all n excursions, and I can say there is many. So if I look at the number of excursions divided by all, like, I've now counted them, but I don't know anymore, like how many were in one of them. It could be that there was just one. It could be that there was like many, many, many in them. And on average, these classes of how they group, they are quite big, because on average there's 4 to the 3 to the length of the excursions, so 4 to the 3 to the 2n, meaning on average there's an exponential number of excursions in each n excursion. So there's many of them. There's a lot of them in them. Okay, so on an average in excursion there's many of them. And now what I want to do, I want to come back to your initial question, Rafik, on the probability of a random n walk to be an excursion. And what do we do now? We can do everything which we did in the beginning. It just becomes more technical with probabilities. What I do, I assign to each of these possible jumps a probability. Let's say the p subscript -1 is the probability for the jump -1. The p subscript 1 is the probability for the jump +1. And the p subscript -1 is the probability for this fork, such that the probability sum to 1, of course. And then the weight of an n walk is just the product of its used weights, basically. And what you can then show is that the probability depends to have an n excursion depends on different choices of your probabilities, basically. So I'm looking at the probability that the random dic n walk of length n is an excursion. So asymptotically, it's asymptotically equivalent, but for p1 and p-1 less than 1/2 to a constant. So there is a non-zero number of n excursions in n walks. If one of them, and I can always exchange p-1 and p1 because it's symmetric. The step set is symmetric in the choice in the ways that you can, depending on what you set them. If one of them is less than 1/2 and the other one is 1/2, then they decay like square root of n, basically. So you've heard something, but square root of n decay. If both of them are 1/2, this basically means that you don't have the fork, because if you set the 1 and the -1 to 1/2, they sum already to 1. So you will never have the fork. And this means you're just a classical dic path. And a classical dic path has this asymptotics, basically. It's an n to the 3/2. And then there's a special third case where you have an exponential growth if one is much lower than one is less than 1/2 and one is bigger than 1/2. And all of these ones, this is answering now what people were interested in networking, because what they were interested in, they wanted to sample models in which they can choose with a certain probability that the endpoint at the beginning are connected. And this is what they can do now, because it's a very simple toy model, but this is the first start so that they can test algorithms. Then they say that the connection behaves like, I don't know, 1/10, or the connection is very, very slow, is like square root of n, or it's very, very big. And in this special toy model, we have now the answer. In this model, this is a model, sample one uniformly at random, flip your coin for each server according to your probabilities. We guarantee you that it will have this connection probability on average, basically, in probability, with high probability. This was what we did for n excursions. So we did some simulations. Because in networking, they were interested in seeing some results and they match our data. So basically here we looked at the equal probability, 1/3. Then it means that in probability to have an excursion, we have already seen it. It's 1/4. This is the green line. So we see the simulations wiggle around and they converge for long paths, basically, on average. This is a theoretical expectation to 1/4, so 0.25. And then we looked at other cases. We have a decay with square root n, or we have a decay with square root n to the 3, basically. And you see they match the simulations quite nicely for some specific choices, if you want to, if you want to look at them. Okay, so is there any questions at this stage? I think I'm much too slow, actually, but yeah. Okay, very good. So what else we want to look at, and let me just briefly show you, not dive into technicalities. Once we have the specification, what I want to do is like look at some parameters to better understand what's the dependency on the probabilities, and now analyze the limiting objects, some limiting laws of these parameters. And what I can do, as in the case of dic n walks, also dic n excursions have an interpretation as two-dimensional lattice paths. That's given here. So for n meanders, basically, we use the previous bijection. We have still these 3 steps. but we have some additional spatial constraints. It's all encoded by the functional equation I derived. So the functional equation for a certain step set is the same as the generated functional equation for my non-deterministic walks. The constraints are like this. The paths have to stay in the first quadrant. They start at 0, they end in the first quadrant. Then we have these paths with some weights. Everything works with weights. And then the x and y-axis act differently. On the x-axis, the path is absorbing, meaning you can never go down. But on the y-axis, the path is reflecting. So if you would go left, the mass is sent back. And this is denoted here by, let's say, P1 plus P minus 1, 1, basically here. And in particular, the n excursions, the one we're really interested in is the ones where x is 0. And if x is 0, the x-coordinate is 0, this means we end on the y-axis. So the ones we're interested in is the number of paths which end on the y-axis, which end on the blue line. And such objects, they have been treated in the literature a lot. It's right now quite a flourishing field. So what is known, for example, if we forget this reflecting absorption and basically make them both absorbing, this is what is classically done. You're not allowing the jump through. Then the generating function is algebraic. Okay, very strong hint that the same will be true here as well. Well, it was true here. And what has been looked at, for example, you can show then easily that if you end on the y-axis, that the endpoint on the y-axis follows a binomial distribution. So how far, if I take a random step path of length n, how far away is it from the origin? Well, I know it's a binomial distribution, so a normal limiting distribution. And we ask now ourselves, okay, what happens in our case, in this special case? So this is what we looked at. And everything depends on the drift. So the drift tells you where is your next jump. So there is a possibility how much will I go to the in the x direction and how much will I go to the y direction in my next jump. So basically this is given here. So the drift just means that so in expectation, how much will I go to the right is 2p1 minus 1, and how much will I go to the left is for dig paths 1 minus 2p minus 1. But we can think of it basically for a given step set, the drift, depending on the weights in your step set, if I jump back here, this tells you, okay, with certain on the weights, the next jump will go up like here or here. Where is the next expected jump going? Where it is sending me, in which direction at least? And the result is a bit complicated, bear with me. But what is quite interesting is we see many phase transitions. It depends on this drift. So if you look on the random variable, such that the final maximum point is an n excursion, then the distance of the final maximal point in this n excursions behaves either is like a discrete distribution, then it changes to a Rayleigh distribution, and then you need to have a non-trivial rescaling. Then it changes into a normal distribution rescaled properly. Then it changed into a convolution of a normal distribution and a Rayleigh distribution. This is on the y-axis. And then it changes again into a normal distribution. And what we see here is like different singularities which become dominant. And this is quite an interesting phenomenon, not observed often, and already interesting by itself here on the level of two-dimensional lattice paths. And what led us here was the theory of these non-deterministic walks, basically. And another law we looked at was the returns to 0. So how often is the reachable points really a singleton, the smallest possible case? And it's always discrete. And it's either geometric, negative binomial, or a mixed type. We can make it explicit, not important what it is. It's just, let me just tell you that, okay, in these cases, it's actually even simple to do it. It just looks a bit more complicated, but it's always a discrete case, which makes sense. But these ones were also interesting for the people from networking. Okay, this is like a bonus, basically. It was a little bit of work, but something, and the simulations match really nicely our results. So the left, you see the final maximal points, the simulation results, basically, and our theoretical results. And on the right, you see basically the limit law for the returns to 0. So basically, in green, we have in blue, we have equal probability. So basically, this is the blue one, which converges improbability to 1/2. Okay. So this is this part. So let me just briefly at the end show you what else can be done, because this was the simplest possible case. This was just dig paths. So a next possible case is like when we in the networking motivation, we don't always force to encode or decode, because of course sometimes you can just say, okay, I just want to stay where I am. I just want to transmit the information further. I don't need to do anything. And this brings us to Motzkin walks. Motzkin walks, they just have a +1, a -1, and a 0. And a Motzkin n walk just has all possible subsets of a Motzkin n-step set. So we have a -1, 0, 1, and then all the other possible jumps combinations, -1, 0, -1, 1, 0, 1, and all three. And here you see an example. Again, it's just a sequence of such steps is a Motzkin n walk. And again, we're interested in what's happening to the reachable points. And here the behavior becomes a bit more complicated. Before, the reachable points were like this, that we have either, they always had a distance 2, they are finite intervals, but always distance 2. And now there's 2 choices, and it's already shown here. They are 2 periodic, because of course you could just use Dick n steps, and they could be 1 periodic. What is like you see here, that between the min and the max, you have all points. And okay, it's not much more complicated. Well, it's different. It's not a complicated case, but it's a second case. But after some technicalities, we can show that the generating function for n bridges, n meanders, and n excursions are explicit and algebraic, and we can do everything with weights, but it's just a bit too technical for the slides and definitely for the end. I have prepared here what happens for specific choices of weights. What we have done, we looked at all weights such that we choose them. So again, we assign weights to each step between 0 and 1, not between 0 and 1, either 0 or 1. We just take it or don't take it. So of all these 7 cases, we looked at all 2 to the 7 of all these cases with a computer, of course, and checked if it's in GeoIS, if there's a nice connection. And there is indeed some connections to lattice paths and to other models. I will skip this now because I spent a bit too much time at the beginning. So this is just like, we've looked at some cases of some 1s and 0s, and some of them are connected to paths on the line, triangle or lattice, or in 3D walks even, which was quite surprising, which we don't fully understand at the moment. So even more connections to 3-dimensional walks for Motzkin and meanders. So if you're interested, this is something we can really dive into if we want to. But at the very end, I want to talk briefly about general walks. This was Motzkin and Dick. So in general, we can do walks. Of course, this is easy. Most of our work was to show that general Dick n bridges are algebraic. So if you take any finite n-step set, the generating function bxyt of n bridges, so we count length, minimal and maximal reachable point, is algebraic. But this was a lot of work. And what's happening here, for example, if you take an n walk here with jumps, this is the walk like -1, 2, -1, 2, -1, 2, 0, 4. You see it on the right. You see it becomes much more complicated. Like everything is a bit mixed. They can cross. The crossings make really complicated things. And what's happening, the reachable points, they were the key. We have to understand them. And here they're much more complicated. But what we could show is, you see it now here on the right, that there is periodicity still in these ones. And what we don't note here is like we have to distinguish 3 different parts, or no, multiple parts, but we call them of 3 different of a type ABC. If there's something happening at the bottom, could be anything, then something is repeated periodically. So like here, the pattern point, point, nothing in B is repeated. Point, point, nothing, a second B, and the point, point, nothing is repeated. And then afterwards, after some repetitions, there's again a part, which is not too big. We can bound it, which can do anything. So meaning at the top and at the bottom, anything can happen, but in between it will be periodic. And then we say that this n walk is of a certain type. And these types, so the types before were simple. We had the type where we had just an interval, we had a jump of 2, or we had jumps of periodicity 2 at full intervals. Here it's much more complicated. And here what we used heavily is a lot of additive combinatorics, which I'm not an expert of, but which is very interesting and very nice and very powerful results, which we were able to use in order to understand these types. Because what is the key to understand this is to understand that there is just finitely many. So what we could show that for any subset of steps you choose, there is finite set of types such that any n walk built from these steps is such that it belongs to a certain type. So the reachable points are of a certain type. And just showing this finiteness, that there's just finitely many reachable points which characterize it, was most of the work. So let me show you in a brief example how this could look like. Oh, no, I didn't show it here because it was already too complicated. But already from this one, we could then show the algebraicity. And then the other ones, n meanders, are simpler, but we could do less. For n meanders, some subfamilies are algebraic. So the ones where we forget about the minimum, we could show that's algebraic. Where we forget about both, this is the ones which return to 0, they are algebraic. But we don't know, the hardest one are n excursions. For n excursions, we conjecture that they're algebraic. We did some simulations, we programmed it, we built a Python package, which is available. If you're interested, you can download it from our GitLab repository to experimentally find the types, and as well more. We need more than just a type. I can show you in a second. We need how the types are connecting, how the walk sends one type to a different type. And we also implemented a lot of Maple packages. So all the computations I've shown you, they are the Maple package, the Maple worksheets are online on my website and on our GitLab package, on GitLab folder. So you can download it and play with it. So in our paper, we always heavily rely on Maple computations because things become complicated quickly. And for these ones, experimentally, we also implemented some guessing of these ones. So at the end, this is one example where we have to jump -1, we have to jump -1, 1, and we have to jump -2, 1. So just 3 of them, and they don't look too complicated. And you can ignore what's here on the types section and so on. But what you have like 8 different types. They are a bit more complicated than what I said, A, B, C. Basically, they are this, up to technicalities. But what we need is, we didn't only need that they're finite, but we need their interactions. And this is this picture, which I just wanted to leave here if there's time, but anyway, I don't want to be too technical at the end. We need the interactions of the types. If you end at a certain type, where does this other step set can send you, and depending on where your minimum and your maximum is. So this is what you need in order to prove that it's algebraic. What I think is true, but we cannot prove it, but we conjecture that it's true. Good. To wrap it up, what we did was just one protocol on a line topology. So of course, the motivation from networking was like other topologies. Maybe series parallel graphs would be a possibility to do next step, to do something more. More protocols, of course. We just did one protocol, of course, and one would like to do more. And what I haven't had time at all, there is a strong link with context-free grammars and with unambiguous context-free languages, which are hidden behind it, which would be maybe a proof strategy. I don't want to spend time now anymore on this. I think series parallel graphs would be possible. More protocols, it's much more complicated. So that's all. Thank you very much for your attention. And I'm sorry that I went over time a little bit. Thank you.
Thank you, Michael, for this nice talk. I'll add some questions, please. So if we can go to slide 10, please.
10?
10, yes.
Yeah.
Okay. What means this coefficient in the polynomial B11T, the coefficient 1763, 583, and so on? What means? What represents?
And what it represents?
Yeah.
It's the number of walks. It's the number of bridges. It's the number of walks in my setting. So meaning the 1 means there's one bridge of length 0 because I start at the beginning. I start at 0. The 7 means there's 7 of length 2. So there are 7 bridges. There are 7 thick end bridges of length 2 in my setting. So if you look at it, you can have a +1, -1. You can have a -1, +1, and then you can combine the +1, -1 steps. So you can have a plus plus, minus minus, and so on. And in total, you have 7 combinations in order to form an N bridge.
Okay.
And then you have 63. So they grow really quickly.
Okay. 9 to the power 10 minus something. Okay. Something to take. Okay.
Yes.
In this same slide, the limit mean the number of n bridge of every length is given. This is a random order. Sorry.
In here, you can interpret it as a random one if they all have the same weight. So every step
Okay.
has the same weight 1 on 3. Here, you can interpret it like this.
Okay.
Or you can interpret you just give them all weight 1 and just count. But here you can interpret it's the same as having it's the same model as in having 1 over 3. It's like choose uniformly at random.
Okay, and I guess it is very hard to obtain some limit distribution of this number. Surely.
It depends what kind of limit you're interested in, basically here. So here it's just counting. They're just counting something at the moment. So what you can analyze is, for example, you could look at how does the minimum and the maximum behave and so on. How many are there of a certain type? But it's not like it depends then on your question of what kind of distribution you're interested in, basically here. So for the moment, it's just here. It was just to focus on the numbers. How many are there? What's their growth? Like how do they behave? And here they are surprisingly simple. Honestly, I have to say I was surprised. We could even derive closed forms here with some basically generalized binomial theorem. You could get something more, if well, more depending on how you want it. But the 9 to the n was the key for us. Was the most interesting quantity here.
Okay. And there is no connection between trees, maybe binary trees and deep work or ambient. There are some connections, bijection, yes or no?
Yes. Yes, okay. Yes.
Okay, so we can use some new results about the trees to obtain.
We could try to connect exactly. We could think of non-deterministic trees, maybe, or something like this, if that, if it would make sense. Yeah. For us, the paths were the most interesting model because they nicely mimic this, this Markovian process that you always continue one more step. You just need to know where you are at a certain time, and then you do one more step. This is the nice recursive property here, which works. But you could look at what's now done, what could be done for trees now. This is definitely possible.
Okay, another possible connection is a connection between these works and maybe polyurus, some polyurus.
Oh yeah.
Where we have two.
Oh yeah. I mean, you could. Yeah. You could assign the probabilities to your encapsulation, decapsulation, or the steps, or something like this. You could make connections with urns. Here, it's less clear what you can do or what's been done. Polyurns are, in a sense, a different framework. But there is connections where people analyze urns with paths. And so it could be that you could mimic, or you could, let's say, reverse engineer a polyurn which behaves like this. But I have to say on the top of my head, I haven't thought about it. Maybe it's possible. Maybe you could reverse engineer something, and maybe it would be interesting to look at it, because then we could create new urns. And this is always interesting because they are very, very useful. Yeah, that's a very good idea.
And another question, if we suppose in these ones that we can move to top by +1, but we cannot make a step of -1, but we can reset to 0. We can return to 0 directly.
You mean from somewhere further top?
For any level, we go +1, or we have two choices. We go to +1, or we down to 0.
Okay.
We go to 0. This can be some results about this one can be obtained. It can be deduced from your results. Possible.
This is a different model, I have to say. I looked at such. It looks very much like something which is in queuing theory sometimes called a catastrophe or something like this.
Yes.
Yeah. And it's a different model. It's different model. So the tools from the kernel method are related or are the same, but they are different in the sense that there you have more structural results which you can use. And it's different models. It's actually different models.
Okay. If you can go to slide 14, please.
Sure, yeah.
1.4.
1.4. Here you go.
Can you give some ideas how you can compute the value of d plus 00t using the kernel method here, because I think you replace maybe 15, maybe the next slide. The next slide.
The next slide? I think not this
No,
one here.
How we can compute d plus 00t?
How you can compute this one? Oh, yeah. This very simple generating function. Basically, what you can do is this is explicit. You see this theorem here on the previous page?
Yes.
So what you have to do, you just substitute x to 0 and y to 0 here everywhere. And basically at the end, if I'm not mistaken, you're left with y of t, because I think y of t on the top right is more or less what remains. Of course, you have to take the limit. You know, here we divide by x divided by y and so on, but it's legitimate to take the limit here. So this disappears. I don't know what happens here. Would need to check what's happening here, but I think you're just left with y of t. So let me just check. Yes, actually, you just have another t here. You see, you have 1 minus square root 1 minus 8t, and this is 1 minus square root 1 minus 8t. So if you take the limit, if everything is explicit, you can do it in Maple, Mathematica, Sage, on your pen and paper, you get this. So that from this, you can get it.
Okay. Last question, slide 20, please.
Thanks. Yes, sure.
About the number of return to 0.
Yes.
Okay. This number, if we are interested to the number of return to 0, it cannot be viewed as Markov chain, and we forget the paths every time that we go to 0. It is like that we have a new wall. We start from 0.
1 second. Do you mean this slide or the one on the final or the returns to 0?
Yes, number of return to 0.
Return to 0. Return to 0.
It is exactly like random, not random one, Markov chain. And every time we go to 0, we forget all the past and we start.
In a sense, we completely restart. Yes, each time. It's like if you have a path which creates something and then it reduces completely to one point, like at the very beginning. And then it continues again and reduces to a full point. Exactly. So you can decompose it in such a way that you always cut here and just need to understand what's happening in these paths. So this is completely true. This is completely correct. And this is basically what we did. This is what we did.
Okay. Thank you. Are there other questions, please?
Thank you very much for these detailed questions. Wow. Thank you.
Other questions, please? So if there are no questions, we have to thank again Professor Michael Wallner for this nice talk, and hope to see you next webinar. Thank you.
Thank you. Bye-bye. Thank you very much. Thank you.